you to see something. Okay. So what is I want you all to pay attention on how the dimensioning is done. Okay. What do I mean by that? I want you all to observe the distance A and 2A, where they get that distance from. Okay. So A, I'm going to sketch this in orange. Okay. The distance A is up to here. Can you see? So it is the center line. Okay. And then from here, 2A is the distance of the structure at the center line. Okay. Center line means it's in between the thickness of the centers. Okay. And then the next one, okay, this is the center line. And then you have the next center line. Okay. So that is the geometry where it is taken. Yeah, I want you to focus on that. Okay. Yeah, very important. Yeah, is not later. Do I need to compensate the thickness? No. The dimensioning. Okay, the dimensioning is done relative to the center line. Okay. I want you all to take note of this. Okay. So the next thing that we are going to do is we're going to construct the shear flow. Okay. So we're going to construct the shear flow. I'm going to use the same diagram. I'm going to construct the shear flow now. Okay. So we know that at the main web, okay, so the shear flow is controlled by the main web. Okay, V, then these are the shear flow direction. And all this, I'm going to call it F1, F2, F3, and F4. And because of the geometry, note F1 is equal to F4 and F2 is equal to F3. Okay. So the next thing that we are going to do is we're going to determine the second moment. So let me write for you the solution procedure first. Okay, let me write for you the so you construct the shear flow first. So the solution procedure. Number one, construct the shear flow. Second one, determine the second moment of area. And then the third thing we do is we are going to apply shear stress is equal to VQ over IT, or Q is equal to VQ over I, either one. Okay. And then the third thing that we're going to do, or the fourth thing now, is we're going to find F will be equal to the integral of the shear stress multiplied by T ds, or we're going to use Q multiplied by ds. Okay. Then after that, number 5, we're going to take moment Okay, we're going to take the moment at point C. Okay, so I'm going to declare this point over here as my point C, right? To find the position of the shear center. Okay. Okay. So that is the procedure we're going to stick to. We have done number one. We're going to find we have already constructed the shear flow. Next, we are going to determine the we're going to determine the second moment of area. Okay. So I'm going to copy this diagram. So now we're going to determine the second moment of area. Okay. So I'm going to draw my transformation first. So this is our y, this is our z. So we are going to find IZZ. So IZZ is twice IAB. Okay. Why twice? Because AB is equal to FG in terms of second moment of area. Then we're going to plus twice IBD. Okay, why? Again, the twice is because the second moment of area of BD is also the second moment of EF. And then we're going to plus IEE. Okay, that's what we will. So we're going to do IZZ. So this is equal to twice. Okay, so knowing that it's ZZ, so this is our width. This direction is our depth. Okay. So IAB. So we are going to call our thickness, because the thickness is all the same. We're going to call it T. Okay. So twice IAB. So the width is T. Right. Then we have A cube over 12. Okay. So now there's an offset distance. So plus by the area. Right. So that's the area, and we're going to multiply by 3A over 2. Okay, we're going to multiply 3 over 2, and this is squared. Why 3A over 2? Because from here to here is A over 2. Okay, and then because this line over here, pardon me, this line over here is our centroid. Okay, so this is 2 IAB, and then we plus again twice. So our width now is 2A. Our depth now is T cubed over 12 plus by 2AT multiplied by A squared. Okay. And then we are going to plus IDE. So the width is T. The depth is 2A cubed over 12. Okay, and you don't need to plus because for DE, the individual centroid and the global centroid are in the same position. Okay, now for this equation over here, want to mention something. So note that A, okay, the distance A is a lot greater than T. Okay, it's a lot greater. I repeat that A is a lot greater than T. So this is now. Hold on. I'm going to make a statement down here. Important statement. So unsymmetrical loading with linear deflection and twisting will only occur in thin wall section. Okay. So some of you ask me, Eugene, how do you know it's thin wall or not? Okay. So what I will say is usually for in this course, I will tell you. Okay. In later, when you're an engineer, right? I'm not there to tell you, or the question is not there to tell you. You have to observe how the structure is deformed experimentally. Okay. Okay. So why all of a sudden I say node A is so much greater than T? This is because this term over here, right? You have T cubed, and when A is so much greater than T cubed, this is approximately equal to 0. Okay, so in that context, you can drop this term. Anything with the T cube, okay, you can drop it. Okay, so let me write out the formula first, okay, or let's see what value we got over here. So IZZ now is equal to twice. So what we have is TAQ or T, or yeah, I'm gonna call TAQ, or I'll do in terms of alphabet. Okay, so A cube T over 12 plus by 9 over 4. Okay, so 9 over 4, right? And this is A cube over T, or A cube T, right? Then plus by twice. This is going to be 2A cube. Okay. And then plus, so 2 to the power of 3 is 8. So this is 4 over 3. A cube T. Let me see. 2 to the power of 3, 8, 4. About no. This is wrong. This is ridiculous. So this is 8. So this 2/3. Okay. So when I calculate, so 9 over 4 plus by 1 over 12 times 2, I get 14 over 3. Wait, do I do this correctly? 3 squared. Okay, hold on. So 9 over 4 plus by 1 over 12 times 2. So this is 13 over 3. Wait, 1 over 12. What am I doing? Plus by 9 over 4 times 2. 14 over 3. A cube T plus by 4 A cube T plus by 2 over 3 A cube T. So this will be equal to 14 over 3 plus by 4 plus by 2 over 3. So I got 28 over 3